So, in our last discussion, we had talked about the vascular changes which accompany acute inflammation, right? And we had finished it. Now, in this discussion, we'll be talking about the next step in acute inflammation, which is the cellular changes. Okay. So, try to understand something. Suppose this is the blood vessel. I had already given you an idea in the last discussion as to what cellular changes or what vascular changes is, but let's recap it once more. So I had said that some microbes or anything which is infected, anything which is a stimulus for the inflammation, some of them will be in the bloodstream itself. Some, very few. They can be easily, destroyed by the circulating WBCs. No problem. Problem is with the majority of the microbes or the stimulus for inflammation, whatever it might be, which are not within the blood vessels themselves. Rather, they are in the interstitial spaces or in the extravascular spaces. To get them, these leukocytes need to leave the blood vessel and they need to migrate towards them. All the changes, all the processes that go on for this to happen, they constitute what we say to be the cellular changes. Okay, so cellular changes is the collective name for all those processes, all those steps that the WBC, that the leukocytes have to go through to migrate to, first of all, get out of the bloodstream from the blood vessel and then migrate towards the source of the infection, which is, in this case, we are talking about microbes. It can be a bacteria, virus, parasite, whatever. These changes are cellular changes. Now try to understand something. There will be few changes. Okay, let me draw another one. It will be better. Suppose this is the blood vessel. So, obviously, the WBCs, first of all, what they will need to do? Suppose these are the WBCs. They first of all need to get out of the blood vessel first. And secondly, these WBCs, they need to reach the source, the microbes. This is the second. These changes, the first one, where the WBCs are escaping from the blood vessel, but they are still within the blood vessel. These are known as the intravascular cellular changes. Okay, and all the processes and all the steps that go on when the WBCs have reached outside the blood vessel, they are known as the extravascular cellular changes. Okay, no problem with that. Okay, so in this topic, in this discussion rather, we'll be talking about the intravascular cellular changes. What exactly goes on as far as the WBCs escaping from the blood vessel is concerned? Okay, all the changes, all the steps, all the processes that happen for the leukocytes to escape from the blood vessel, that constitutes the intravascular cellular change, and that we'll be talking about in this discussion. Remember what the vascular changes had accomplished, by the way? The vascular changes were meant for, just a quick recap, the vascular changes were the initial response, that is, a reflex vasoconstriction so that the blood flow is limited, but then mediator induced vasodilation so that there is more accumulation of cells and proteins at the site of inflammation, and then there was the formation of exudate so that obviously the WBCs can escape. So all of this is so that the body can limit first of all, the infection, and second of all, so that the leukocytes can be sent to the source of disturbance. That is what inflammation is, right? Apart from these two things, there is another thing that inflammation is about, which is the initiation of repair. That we won't be talking about right now. So this is the general overview of how inflammation works, and this is where cellular changes comes into play. Now let's talk about the intracellular, or the rather intravascular cellular changes. So what happens in that? So let's talk about that. What is happening in this case is something which we call to be leukocyte recruitment. Now listen to me very carefully. Again, for the third time, let's draw a blood vessel. Suppose this is a blood vessel. Okay. In normal blood flow, what happens is that the blood cells, they actually more or less, they are following a streamlined, a laminar flow, right? This is the laminar flow. Let me write it down. So in the laminar flow, what's happening is that the blood cells themselves, they actually kind of constitute a central, you might say, axis. They're flowing more or less along a central axis throughout the lumen. Whereas the fluid part, suppose this is the fluid part, that is more concentrated towards the periphery. But this is the laminar flow. This is how normally blood cells flow. But we don't want this. Why? Because we want that the blood cells, or to be more specific, the white blood cells, they should come towards the periphery. Because we subsequently want the WBCs, we want the leukocytes to escape, to go out of the blood vessel, right? And to achieve that, the white blood cells need to kind of sacrifice their central flow and come towards the periphery. We want that. But how will that be achieved? To achieve that, there are a few factors that we need to count in. First of all, we need to understand something. What is that first thing we need to understand? The first thing that we need to understand is that WBCs, they already have a tendency, even in the normal laminar flow, they have a tendency to kind of marginate or come towards the periphery. Why? You might ask. The reason for this is, suppose this is a capillary. Okay, and this kind of is a post-capillary venule. WBCs, we know that they are larger. They are larger than RBCs, right? As such, RBCs, which are smaller, they will move faster. They move faster, and hence they are even more centrally, you might say, located, or even more central in the axis of the laminar flow. So even in the laminar flow, we said that the cells, more or less, they are constituting the central axis of laminar flow, and the fluid part of the blood, that is more towards the periphery. But even within the cells, some will be more towards the periphery and some will be even more central. Red blood cells, being smaller, they are faster. They flow faster than the white blood cells. So they kind of have a tendency to be even more centrally located, and white blood cells are Obviously, all of them are within a central axis, but even within that, there is a tendency for white blood cells to kind of go towards the periphery because they are larger and hence they are not as fast as red blood cells. This is kind of aggravated, number one, in two conditions. Number one, when from capillary the blood is going to the venules, because here, try to understand, the red blood cells, since they are kind of fast, so they will keep moving in the central axis. But the white blood cells, which were kind of, towards the periphery, when they reach the post capillary venules, they have a tendency to go towards the lumen or towards the margin, because they are not as fast as the red blood cells because they are larger. This is in the normal condition. But in inflammation, since we have said that there will be something known as stasis, this stasis will kind of increase the tendency of WBCs to go towards the margin. This going towards the margin, This going towards the margin, this has been given a special name. This is known as margination. Okay, so this is called margination. Margination is said to be the first, you might say, step in the intravascular cellular change. Margination of what? Margination of leukocytes. So there are two factors that we need to count as far as margination is concerned. Why are the white blood cells being marginated? Why are they kind of leaving their comfort zone of the central axis flow in the laminar flow, and why are they coming towards the periphery? There are two reasons. Number one, even in the normal laminar flow, WBCs already have a tendency to come towards the periphery because they are larger, hence a little slower than the red blood cells. Even then they are pretty fast, but compared to the red blood cells, they are a little slower. So that's why from the capillaries to the post capillary venules, when the blood is coming, red blood cells, since they are very fast, they are not quite affected by that increased space of the lumen. But white blood cells, they are a little slow, and they will see that, oh, I'm getting a little more space now. So they kind of have a tendency to marginate, but they don't actually marginate in the normal laminar flow. This tendency to marginate increases a lot due to something called stasis, which we have talked about in our previous discussion. What was stasis? We had said that when inflammation is going on, due to the vascular permeability increase, there will be exudate formation, right? So exudate formation means a lot of fluid will go out, and the resultant or the remaining blood will become a lot thicker, and so the cells will kind of have a tendency to settle down. Cells tend to settle. Now this cells means blood cells, so that does not only qualify for white blood cells, this also means platelets and other clotting factors. So this means that stasis is also another important aggravating factor for thrombus formation, which we'll talk about later in a subsequent chapter. Okay. Anyway, so stasis, due to the blood flow now becoming kind of static, the white blood cells now have, their speed will slow down, and they will have an increased tendency to marginate and come towards the periphery. So this is the first step in the, you might say, leukocyte recruitment, or in the intravascular cellular change, margination. Now let's talk about the second step. Again, align. Now what's happening is the white blood cells are now kind of marginating, but they are still pretty fast. So Okay, let's kind of name this point as capital A, and now we are dealing, so margination is capital A point. Now we are going towards the B, the second point or the second step. So yeah, now like I was telling, even after being marginated, so the white blood cells, they have now kind of come towards the periphery, but even now they're moving pretty fast, but we don't want that. So we want the white blood cells to slow down, and then we want the white blood cells to stop completely. The stopping completely is the third point. Second point we are talking about right now, that is a slowing down of white blood cells. How does that happen? That happens due to the interaction of certain, you might say, proteins or glycoprotein and receptors. More or less what I'm trying to say here is certain molecules. Molecules of what? Interaction of the molecules of what? Interaction between the molecules of obviously leukocytes and what cells margin the, or what cells are present at the margin of the blood vessels? Endothelial cells. So endothelial cells. So there are certain molecules which are expressed on the surface of leukocytes, and there are certain molecules which are expressed on the surface of endothelial cells. These molecules interact with each other, and this leads to kind of a speed breaker kind of a simulation. So speed breaking kind of simulation, you might kind of imagine that these are speed breaks for the white blood cells, which have been pretty fast until now, but now they need to slow down. What are these molecules exactly, and what is this step called? We'll come to that later. What are these molecules? The molecules which are expressed on the leukocytes for this purpose, they are sialylated oligosaccharides. Okay. The most common example for this is something called sialyl Lewis X. Sialyl Lewis X. This is actually an oligosaccharide which is sialylated. Okay. So these are, you might imagine them to be certain molecules which are expressed on the surface of leukocytes, and they bind to their complementary, you might say, molecules on the endothelial cells, which are a family of glycoproteins known as selectin. A very famous, you might say, selectins. These molecules, they express on the endothelial cells, and the interaction between the sialyl Lewis X and selectin, that leads to the slowing down of the leukocytes. Now, due to the slowing down of leukocytes, what happens is, suppose this is the, you might say, one of the boundaries of the blood vessel. Okay. So these are, suppose, the endothelial cells. Okay. Now, endothelial cells, as I had mentioned, they are expressing selectin. So suppose this is the selectin, and the white blood cells, they initially they were kind of here, then after margination they come close towards the margins, towards the periphery. So now they are here, but they are still pretty fast. To slow them down, they kind of express sialyl Lewis X. Let's suppose this is the sialyl Lewis X. Yeah, let's write like that. Okay. So these are the WBCs, and they actually express the sialyl Lewis X. And these are the endothelial cells. They are expressing selectin. Okay. So the interaction between these two molecules, that tends to slow down the white blood cells. So next what will happen is the white blood cell that will actually kind of start to tumble over the endothelial cells. So then suppose over here there were some other sialyl Lewis X molecules. So next what will happen is it will kind of roll over, because now it is slowing down. So it will kind of roll over and okay, it is rolling over the endothelial cells due to the, you might say, loose adhesion between selectin and sialyl Lewis X, or the sialylated oligosaccharides. So this step of speed breaking the white blood cells, not into a complete halt, mind you, this is kind of a loose adhesion. This is loose adhesion, not firm adhesion, but loose adhesion. This step leads to something called rolling. Hence, this step is called rolling of white blood cells. So rolling is actually a loose adhesion in between the subsequent complementary molecules expressed on the leukocytes and the endothelial cells, which leads to the slowing down of the otherwise very fast moving white blood cells, which had previously marginated already. Okay, so first there was margination, then there is rolling. Now we need to understand something else as well as far as rolling is concerned. In a normal white blood cell and in a normal endothelial cell, these molecules, sialylated Lewis X, sialyl Lewis X, or the selectin family molecules, these are not as numerous, or these are not expressed at all in the normal white blood cells or in the normal endothelial cells when there is no inflammation. However, when there is inflammation, in case of inflammation, there is the release of, I have already talked about this a little, we will talk about this in much more details later, certain chemical mediators. Okay, these chemical mediators at the site of inflammation, especially something called the cytokine family, especially, what they will do is they will kind of induce these expression of sialyl Lewis X or selectin on the surface of the leukocytes and the endothelial cells. Okay, so this is how our body ensures that under normal circumstances there is no chance of either margination, or even if there is margination to some extent, because I had mentioned that in normal cases there is a tendency for margination, but there is no chance of rolling because there isn't enough expression of selectin or even of sialyl Lewis X molecules. So there is nothing to bind to as far as the leukocytes and the endothelial cells are concerned. They are only expressed as the cytokine family of chemicals or molecules, which are chemical mediators, very potent, but they are not the only chemical mediators which actually lead to this. Histamine might also lead to expression of these molecules, but cytokine family is the most potent. Anyways, so they are actually inducing the expression of sialyl Lewis X or selectin molecules, which lead to their interaction and hence the slowing down of white blood cells and subsequent rolling. A little bit more about these individual molecules. First, sialyl Lewis X, there isn't much to talk about. We will talk about sialyl Lewis X later when we'll talk about leukocyte adhesion defects, but for now there isn't much to talk about it. But there is a little to talk about selectins. Okay, so selectins, what are they exactly? Selectins are actually, as I had mentioned before, that they are glycoproteins. Okay, so they are kind of glycoproteins, and this selectin is a family which is actually constituted by 3 major members. One is called P-selectin, E-selectin, L-selectin. Okay, P-selectin is expressed in platelets and endothelial cells. E-selectin is expressed in endothelial cells only. L-selectins are expressed on majority of leukocytes. So it is not just sialyl Lewis X, or it is not only endothelial cells which express the selectins in case of rolling, but some WBCs, or rather majority of WBCs, they also have some what? L-selectin. And L-selectin also has complementary, you might say, white, or let's go with something else. So this also has complementary receptor on the endothelial cells. Mostly it is actually given by, I think, CD34. So this L-selectin will actually, which is on the WBCs by the way, the L-selectin, that kind of binds with its complementary receptor, which is CD34 on endothelial cells, whereas P-selectin, this is suppose this is P-selectin and this is E-selectin, they bind to sialyl Lewis X. Okay. So I'll later, when we finish this off, we'll make a table and then we'll list down all these molecules and their complementary receptors and stuff like that. Okay, so we'll all conclude with jotting down all these points. Anyways, so for now, let's go back. How will you remember this? P-selectin, E-selectin, L-selectin. There is a trick to remember this, or rather there is a trick to remember what these selectin families individually are present on. When you say E, obviously endothelial cells. When you say L, obviously that means leukocytes. But when you say P, you mean platelets. But how do you remember endothelial cells? Very simple. When you say P, you're automatically pronouncing E, right? So P is how do we actually pronounce P? Like P. So PE, P. So P for both platelets and E for endothelial cells. Okay. So these are the 3 major families. Okay, and what is seen is normally, as I had already mentioned, and I'm repeating the point again, normally they are not expressed, or normally they are present in very small numbers on the surface of the subsequent sources. It might be endothelial cell or it might be leukocyte, whatever. But upon exposure to the chemical mediators, which can be histamine or any kind of cytokine, for example, if I am to give an example, TNF or interleukin 1, these are very important for the expression of the selectin family. Okay, so these actually, upon exposure, what happens is the selectin, actually there is another point that you can remember. These selectin molecules, what happens is they are in their inactive state, they are present in certain intracellular bodies, which are called intracellular Weibel pallid bodies. What are they? Weibel pallid bodies. What does that mean? So suppose this is the cell, can be an endothelial cell, can be a leukocyte, whatever. Within them, when it is inactive, the cell has not been activated, in certain intracellular body, the selectins are present. Or how I had given this, right? Yeah. So the selectins are present like this. This is the Weibel pallid body. But upon exposure of, suppose TNF or interleukin 1 cytokines, what will happen is these selectin molecules will come up to the surface and they will be expressed in large numbers in the surface, or rather on the surface. Surface of what? Surface of, it might be an endothelial cell. If it is P and E selectin, it's endothelial cell. If it's L selectin, it is the leukocytes. Okay. So Weibel pallid body. Done? Done. So this is what results in the slowing down of the leukocytes. Now obviously something that you can already jot down, or something you can already note from this, is that the interaction between the sialyl Lewis X molecules or the L selectin and the subsequent P selectin or E selectin or the CD34 molecules, all these molecules which are actually participating in rolling, the interaction between them isn't strong enough to completely stop the white blood cells right at their tracks. So they will still keep moving, but they have slowed down considerably. And now since they're kind of moving over the endothelial cells, kind of tumbling over the endothelial cells, so we say that they're kind of rolling over the endothelial cells. So first came margination, then came rolling, and now we come to the last step in the intravascular changes, or not the last step, but the second last step, you might say. So what is that? So that is complete stoppage of the WBCs, of the leukocytes. How is that achieved? That is achieved again by interaction between some molecules, but this time the molecules are different. So they are not the same molecules as the rolling ones, they are different. What are those molecules? They are integrins, the integrin family. The integrin family molecules, they are expressed on the leukocytes, and interaction between integrin family molecules and certain molecules which are simply said to be adhesion molecules. Adhesion molecules on the endothelial cells. The interaction between them is very strong, and this tends to stop the white blood cells completely. Okay. Before going into the details of each of these two kinds of molecules, again, it is pretty easy to understand this, that under normal circumstances, obviously you won't find integrin molecules on the surface of the leukocytes, you won't find these adhesion molecules expressed on the endothelial cells, or even if you do find them, they will be expressed in very low concentration, so that they do not affect the normal laminar flow of the white blood cells. So only in inflammation sites, white blood cells tend to marginate, roll, and completely stop. This step is known as adhesion. Okay. So mind you, this is adhesion, or you might say firm adhesion, because I had said that in the last step, rolling was also an example of adhesion, but it was loose adhesion. Loose adhesion, we don't normally refer to that step as loose adhesion, we say it's rolling. But this step is known as firm adhesion, or you can say only adhesion. Okay. So again, what exactly stimulates the white blood cells, stimulates the endothelial cells to express these very special molecules? The answer is again chemical inflammatory mediators. Mostly chemokines. Chemokines, they are also an example of cytokines. So they also belong to the family of cytokines, but they are a little special. As the name suggests, chemo means it has something to do with chemoattractant property. So chemokines are actually the family, or they are a member of the family of cytokines. They are molecules, or rather a class of molecules which are chemoattractant. As we will see later, the white blood cells, after they have migrated, or rather after they have escaped from the blood vessel, they are attracted towards the source of all those disturbances and infection and inflammation, whatever you might say, the microbes, because the microbes tend to be secreting some very special chemicals which are chemoattractant. One very special example of that chemoattractant molecule is chemokine. There are other examples as well. So chemokines, they are inflammatory mediators, and they seem to be affecting the WBCs at this stage, forcing them to, or rather stimulating, not forcing, forcing is a little strong word, but they are kind of stimulating the WBCs to express integrin molecules. Okay. And for obviously the adhesion molecules, again, the other cytokines. Okay. So cytokine family has a very large role to play in the expression of these molecules in the cellular changes of inflammation, right? We will talk about all of these in a lot more detail in subsequent discussion. Anyways, now obviously integrin is a family, and there are a lot of molecules which are example of this. So integrin family, one example can be CD11, CD18, another example can be VLA4. I don't remember this, I'm actually kind of looking at the book and writing these. So but the point is that they are all integrin molecules. They will actually bind to adhesion molecules. Now these adhesion molecules I had mentioned here, this you need to remember. Majorly in this case there are two adhesion molecules which are very important. What are they? ICAM1. ICAM1 stands for intercellular adhesion molecule. No problem. Intercellular adhesion molecule 1. And another example is VCAM1. Vascular vascular cell adhesion molecule. CD11, CD18, these integrins interact with the ICAM1, whereas VLA4, this integrin actually interacts with the VCAM1, VV. Okay, vascular cell adhesion molecule, and the integration in between them is very firm, very firm, and this leads to what? Complete stoppage of the white blood cells. This concludes the firm adhesion. So now the white blood cells are completely stopped at their tracks. So then we go to the last stage of intravascular cellular change. What is that? Last stage is, as you can kind of understand, the migration of the white blood cells. Now they have completely stopped. All they now need to do is dig out through the endothelial cells, through the basement membrane of the blood vessel, and they will be free. This step is called transmigration. Transmigration. So what is transmigration exactly? Obviously, as you can understand, that after the white blood cells they have been arrested, what they will do? The WBCs will migrate through the vessel wall, okay, by a process which is called transmigration. And since they are squeezing through the vessel walls, so that is known as diapedesis. So transmigration is also called diapedesis. Okay. Transmigration or diapedesis, a very important point about them is that they occur primarily in the post-capillary venules. Okay, this is an important point to remember. They occur primarily in post-capillary venules. However, again, there is an exception to this. An exception is in case of pulmonary circulation. In case of pulmonary circulation, it has been seen that they can also kind of squeeze their way out through capillaries. Okay, so normally venules, and by the way, I had actually forgotten to mention this, I saw this later. Post-capillary venules is also the common site where vascular permeability changes actually kind of occur. So venules are very important because they seem to be the primary site of all these changes that are occurring as far as inflammation is concerned. Vascular change, in that we had an alteration of vascular permeability. In that case also, post-capillary venules is the most common site where that occurs. And in the cellular change case also, transmigration, diapedesis of WBCs, that also seems to be occurring primarily in post-capillary venules. The only exception being pulmonary circulation, where it tends to primarily occur through capillaries. Okay. Now, this squeezing out through the endothelial cells, this is actually helped kind of mitigated by interaction of, again, another molecule. That molecule is CD31. Interesting thing about CD31, there are two interesting things. Number one, CD31 is expressed where? That is one interesting fact. It is expressed on both leukocytes and endothelial cells. So here the interaction is between the CD31 of both leukocytes and endothelial cells. So this is an example of homotypic interaction. Very interesting. Homotypic interaction. Another interesting thing about CD31 is the name of CD31. There is an alternative name for CD31. It is also known as PCAM. PCAM. PCAM means platelet endothelial cell adhesion molecule. Platelet endothelial cell adhesion molecule. So, interaction between the PCAM of leukocytes and that of endothelial cells, which is a homotypic interaction, that tends to mitigate the diapedesis process. And after it has squeezed through the endothelial cells, try to remember something, very basic biology, that the endothelial cells, they are what? they're resting on this red line that I have drawn. This, what is this? The basement membrane. So not only do you have to squeeze through the platelet, through the endothelial cell, but you also need to dig out of the basement membrane. So for achieving that, collagenase enzyme that is actually used. Okay, so collagenases are used by WBCs to dig out. Okay, after the WBCs have reached, suppose the WBCs are now here. So first there was margination, there was rolling, then there was firm adhesion, then there is transmigration or diapedesis. These four constitute the intravascular cellular changes. After the WBC has escaped from the blood vessel, now it needs to reach the disturbance, the microbes, the bacteria, the virus, the parasites, whatever. All the changes that are occurring here and the subsequent killing of the microbes as well, this is what comes under extravascular cellular change. And that is something that we'll be covering in the next discussion. So I hope that you found this discussion to be somewhat stimulating and somewhat informative, and I'll see you guys again later. Again, I'm trying to make videos very regularly now. So anyways, thank you for sticking, and yeah, I'll see you later. Bye.